Good morning, students. Today we will do the theorems based on linear operators. So in the first theorem, we will show that the range and null space of a linear operator are vector spaces. So the theorem is, let T be a linear operator, then prove that the range of the operator T is a vector space. The range is denoted by RT. And in the second part, we prove that if the dimension of the domain of T is finite, then the dimension of range, that is at most n, where n is the dimension of dt. dt means domain of T. And in the third part, we prove that null space of T, that is also a vector space. So first of all, we prove the range of the linear operator T is a vector space. So in order to prove RT is a vector space, let us take two vectors y1 and y2 belonging to a range of T and two scalars alpha and beta from the field of scalars. Now we prove that alpha into y1 plus beta into y2 that belongs to the range of T. Now because the vectors y1 and y2, they belongs to a range of T. So by definition of range of T, y1 will be of the type of image of x1 under T, where x1 is an element of domain of T. Also y2 belongs to RT, means y2 will be of the form of image of an element of domain of T. So we can take y2 of the form T of x2, where x2 belongs to dt, means domain of T. Now x1 and x2 belongs to domain of T, and alpha beta are scalars, and domain of T, that is a vector space. So by definition, alpha x1 plus beta x2 will belong to domain of T. And by definition of T, because by definition of T, the image of this element that belongs to range of T. So T of alpha x1 plus beta x2 belongs to a range of T. Now let us use the linearity of operator T. Because T is linear operator, so by definition of linear operator, T of alpha x1 plus beta x2 is equal to alpha into image of x1 plus beta into image of x2. Now image of x1 under T is y1, image of x2 under T is y2. So we have obtained T of alpha x1 plus beta x2 is equal to alpha y1 plus beta y2. Now from here, because this belongs to RT, so we can say that this vector belongs to RT. And by definition, this proves that range of T is a vector space. Now in the second part, we are given that the dimension of domain of T, that is n, which is finite, and we are to prove that the dimension of range of T is at most n, means the largest linearly independent set of vectors in RT that should consist of n vectors. It means if we take more than n vectors in RT, then the set consisting of those n plus 1 vectors should be linearly dependent. So let us take a set of n plus 1 vectors y1, y2, y3 up to yn plus 1. These are n vectors in a range of T. Now we prove that these vectors are linearly dependent. Now because y1, y2, y3 up to yn plus 1, they belongs to range of T. And by definition, range of T is a set consisting of the images of the elements of domain. So y1 will be the image of some element of domain of T, and that element we have taken x1. So we can take y1 is equal to t of x1, y2 is equal to image of x2 under t, where x2 belongs to domain of t. Continuing like this, yn plus 1 is the image of an element xn plus 1 from the domain of t. So yn plus 1 can be written as image of xn plus 1 under t. Now these n plus 1 vectors x1, x2, x3 up to xn plus 1, they belongs to domain of t, and the domain of t has the dimension n. We are given in the statement dimension of domain of t is finite, and that is n. It means the largest linearly independent set in this domain of t, that is consisting of n vectors. It means these n plus 1 vectors, they form a linearly dependent set. Now by definition of linearly dependent, if we take their linear combination is equal to 0, then not all the scalars will be 0. So we can say there exist scalars alpha 1, alpha 2, alpha 3 up to alpha n plus 1, not all 0, such that their linear combination alpha 1 x1 plus alpha 2 x2 and so on alpha n plus 1 xn plus 1 is equal to 0. Now operating by t on both sides of this equation, so this side will become t of alpha x1, alpha 1 x1 plus alpha 2 x2 and so on alpha n plus 1 xn plus 1, and on the right side t operated on 0 vector, that will be 0. Now because t is a linear operator, so by using the properties of linearity of t, this will become alpha 1 into image of x1 plus alpha 2 into image of x2 and so on alpha n plus 1 into the image of xn plus 1 is equal to 0. Now image of x1 under t, that is y1, image of x2 under t, that is y2, image of xn plus 1 under t, that is yn plus 1. So from here we get alpha 1 y1 plus alpha 2 y2 and so on alpha n plus 1 yn plus 1 is equal to 0. Now here not all the scalars are 0. So by definition the set consisting of the vectors y1, y2, y3 up to yn plus 1, that is linearly dependent set. Thus we have proved that any set consisting of more than n vectors in the range of t is linearly dependent. It means we can say that the number of elements in the largest linearly independent subset of Rt, that is consisting of n vectors. So we can say the dimension of Rt is less than or equal to n. Now in the third part we are to prove that the null space of T is also a vector space. So let us take two vectors x1 and x2 belonging to null space of T and two scalars alpha and beta. We are to prove that alpha into x1 plus beta into x2 belongs to null space of T. Now because x1 belongs to null space of T, by definition the null space of T consists of all those vectors whose images under T are 0. Now because x1 belongs to null space of T, so by definition of null space the image of x1 under T, that will be 0. Also x2 belongs to null space of T, so by definition image of x2 under T, that will be 0. Now because we are to prove that alpha x1 plus beta x2 belongs to null space of T, it means the image of this vector under T, that must be 0. So let us find the image of alpha x1 plus beta x2 under T. Now because T is linear operator, so by using the property of linearity, this will become alpha into T of x1 plus beta into T of x2. Now t of x1 is 0 and also t of x2 is 0. So we get the image of alpha x1 plus beta x2 under t is 0. And by definition, this vector alpha x1 plus beta x2 belongs to null space of T. So this proves that null space of the linear operator T is a vector space. Now, an immediate consequence of the part B of above theorem is given here, which states that linear operators preserve linear dependence. It means if we have a linearly dependent set of vectors, then their images, they under T also forms linearly dependent set. So let us take T is a linear operator from dt to Rt. This be a linear operator, dt is domain of T and Rt is the range of T. And let us take a linearly dependent set in domain of T, which consists of the vectors x1, x2, x3 up to xn. Now because these are linearly dependent vectors, so by definition we can take scalars alpha 1, alpha 2, alpha 3 up to alpha n, not all 0, such that the linear combination will be 0. So we get alpha 1 x1 plus alpha 2 x2 and so on, alpha n xn is equal to 0. Now let us operate by t on both sides. So here operating by t on both sides, we get t of alpha 1 x1 plus alpha 2 x2 and so on, alpha n xn is equal to 0. Now because t is linear operator, so by using the properties of linearity, this will become alpha 1 into t of x1 plus alpha 2 into t of x2 and so on, alpha n into t of xn is equal to 0. Now this is a linear combination which is equal to 0 and not all the scalars are 0. So by definition we can say that the vectors t of x1, t x2 and so on, t of xn, they forms a linearly dependent set in the range of T. So this proves that the linear operator preserves linear dependence.